So good afternoon, everyone. So my name is Vibhor Saraf. I am from STMicroelectronics. So I'll be presenting my paper on the title is On Chip All Digital Low Mismatch CMOS Process Monitoring Sensor Circuit for Accurate Process Sensing in 28 FD-SOI technology. So the next few minutes, the presentation will be flowing with the following agenda. And so coming to the intro. So the question is like, what are process monitoring circuits? So process monitoring circuits helps in defining the process on silicon and helps us circuits help us in the process binning. So process binning, and it also helps in the to apply the compensation during the design. So I will be covering about the different compensation techniques which we apply during the design. So as you can see in the picture, these sensors are designed and deployed within a product at multiple locations on the chip. So to have the wider coverage and accurate process estimation. So this is a full wafer, and we have the multiple chips, multiple dies present, and the circuit is present on the chip. Now coming to the problem part. So today, we have multiple process monitoring circuits in the market. Like we have analog circuits, we have scribe structures, and we do have digital circuits. So they come with their merits and demerits. So in analog, we have integration challenges. So to integrate in the system, it's a bit complex, and they are less precision, and they require more area, and they do require the regular calibration. Coming to the scribe structures, so the problem with that, they will be destroyed during the wafer binning. So we cannot use in the real time after binning. And coming to digital, so they are easy to integrate, and they are ring oscillator based structures, and they have the high precision and can be used for real-time monitoring. I will be focusing on the digital. So my proposal is the digital circuit. And so now in VLIC, we see with the scaling of technology, circuits have become complex, and the manufacturing is becoming more complex day by day. The non-uniformity of transistors and their characteristics producing timing variations in the circuit, which reducing the timing margins, the SRAM read and write margins, and the high leakage currents. So which incurs which are directly giving the yield loss. And the yield loss is the money loss, basically. So the problem, this is the circuit which I have taken the closest reference to the proposal. So the process monitoring circuits which I have encountered is the we have taken for consideration are the ring oscillator based structures, and as the geometry is shrinking, so there is high mismatch in the small transistors, in the small transistor dimensions, and because of the mismatch, the reading from the sensors become is not reliable, and there will be chances of inaccuracy. So as you can see in the closest reference in our circuit, so because there is a contribution, the mismatch is coming from the insensitive transistors. Because of that, there is a accuracy problem, and we are actually solving this problem in our circuit. Now, as I mentioned about the compensation techniques, which the circuits helps in the to tell what compensation you need to apply. So with the unreliable data from the sensors, we may lead to have error in the post-silicon compensation techniques like AVS or ABV. So AVS stands for adaptive voltage scaling, and ABV stands for adaptive body biasing techniques. And it may also lead to incorrect process binning, which can affect the yield, or we can say we can over design the circuit, or we have not designed the circuit at the maximum performance. So coming to the proposed solution, so this is a figure. These are two circuits now. So I will be explaining the working of the first circuit, which is the NMOS based circuit. Now, in this circuit, what we are doing is we are converting the on current of the NMOS into the delay. And so basically we're utilizing the on current of the MOS to pull down or pull up the capacitance, what we are charging and discharging. Now, the figure is shown for the NMOS processing matrix sensor. Now, the working is follows as when the input is logic low, like input means when in underscore N node is logic low, transistors M2, M3, M4, and M8 turns off, and M1, M5, M6, M9 turns on. So during this time, the transistor M7, which we can see is it's a MOSFET cap, is an N-type MOS capacitor. It will charge through the on current of the transistor, which will charge to the M1 transistor, and at the same time, M8 transistor will cut off. So M8 transistor will cut off the output node from the capacitor node. So, and as you can see, when my input is logic low, in underscore N is logic low. So at that time, M9 is on. It's a PMOS transistor. So it will immediately pull the output node to the logic 1. Now, so I had given the input as logic low, and very you can say with the very less time, I have got the output as 1. So there is a rise time which is very less. Okay. Now, when the input is logic high, when we are giving high input, so transistor 1, 5, 6, and 9 turns off. Okay. And transistor 2, 3, 4, 8 turns on. So during this, the pass transistor, which is M8, creates a short circuit path between the output node and the capacitor. So basically, earlier we charged the capacitor. Now we'll be discharging the capacitor through the stack of this NMOS. So, now the NMOS M4 will start discharging this capacitor, but it will start. The transistors are configured such that it will discharge gradually, which will result in the higher fault delay compared to the rise delay. As you can see in the waveform, so we have given this when we are given the logic low input. So we are given we have got the immediate high input, so high output, and we are giving the when we are giving the high logic high as an input, and we are getting the fall time as large value. So the time required by the transistor M4, which is a large cap, sorry. Yeah. So basically, this is a transistor which is discharging my cap basically. So the time required by the M4 to discharge the capacitor can be used for sensing the on current of the NMOS. And since the output frequency is now majorly governed by the NMOS process, so we can say the NMOS on current can be captured through this NMOS current on current shift can be captured through this behavior. The adjacent figure is for the PMOS, and the working is similar as the NMOS. So to validate this, we have run the Monte Carlo simulations 10,000 points, and so these are the results. So at 0.8 volt and the temperature range of -40 to 150 degree, so we see the mismatch. In the reference circuit, there was a mismatch of 15.73. So this mismatch is a 3 sigma variation. It's a global mismatch value, and it's a 3 sigma variation. So the idea was we have to reduce the mismatch value, because this mismatch was coming from the unintended transistors, which was a PMOS in case of NMOS sensing circuit. And we are successfully able to reduce this mismatch from 15.73 to 4.65. And so finally, we are achieving the 3 sigma global variation, which is within 5%, and there is no area overhead as such. Now coming to the silicon results. So this circuit is validated on silicon, and we can see the results here for temperature 30 and temperature 150 degree. These above 2 figures are for NMOS, and below 2 figures are for PMOS circuit. And we see in the figure at different voltage and temperature conditions, silicon behavior is aligned to the typical simulation, which is done on the CAD. And so this signifies the good model hardware correlation, which in turn validates the model accuracy which we are using. So good silicon model hardware correlation will give will lead us the accurate process binning. We will be able to do the granular process binning, so that we will be able to now signify we will be able to define the process very granular. like this is SS, TT or FF, or within TT to SS, we'll be defining this is 1 sigma, 2 sigma, and 3 sigma processes, so that we will not be able to over design, so that it will penalize our performance or power. So with the conclusion remarks, so we have converts the on current delay, on current into the delay, and offers on-chip process, on-chip operation, and we basically becoming the overcoming of scribeless structures. And the proposed circuit has a significant improvement sensing accuracy by reducing the impact of non-sensitive elements on the output frequency, which is less than 5%. Moreover, so the proposed circuit which we have proposed, it occupies the area of 0.96 micrometer square, therefore offering a substantial reduction in the area required implement the sensor. And so the reduction is the reduction in area will reduce the footprint on the chip, which will reduce the cost as well. And so the proposed circuit, what we have done, we have taken the 60 stages of this NMOS circuit and 84 stages of the PMOS circuit in a ring oscillator fashion to have the considerable frequency. And the worst case power we have got is 600 microwatts. This is a leakage power, worst case leakage power at 0.8 volts. So which is making the sensor suitable for integration in a wide range applications where area and power are more crucial. Yeah, these are the following references. Yes, thank you.